Hi everyone, welcome back. In this particular video, we're going to summarize the use of hydridic reagents like sodium borohydride and lithium aluminum hydride for converting carbonyl compounds into alcohols or synthesizing alcohols from carbonyl compounds. Now, both of these reagents are suitable for synthesizing an alcohol from a carbonyl compound because when you react a carbonyl compound with sodium borohydride in a polar protic solvent, for example, an alcohol, or when you react the carbonyl compound with lithium aluminum hydride in THF followed by an acidic workup, your product is an alcohol. The key thing to remember here is that the nature of the alcohol that is formed is determined by the carbonyl compound that you start off with. So I've noted that down here. The carbonyl compound determines the nature of the alcohol product. And I'm going to use these examples here to sort of show you that, demonstrate that, okay? So if the carbonyl compound that we're using is formaldehyde, then the product that you're going to get is going to be methanol. There is no other variation possible here, okay? So let's see that. So if I start with formaldehyde, and let's choose the example of sodium borohydride here. And again, remember that the borohydride is, the sodium borohydride is a source of nucleophilic hydride. That's what it supplies, okay? This boron is negatively charged. The hydride is going to come and attack the carbonyl carbon. The double bond gets pushed over. And so by the end of it, what we get is we're going to get CH3 with an O minus. Okay, we basically get methoxide. Okay, this carbon has another hydrogen added to it, so that's CH3, and then that oxygen is an O minus. And then in the subsequent step, this methoxide could deprotonate the solvent because methanol is our solvent for doing all of this, or it could be another polar protic solvent. Okay, it's going to deprotonate and it's going to give you methanol as the product. Now, so this almost seems redundant because if you're using methanol as a solvent, why would you want to make more methanol? That is true, right? But I'm just trying to show you as an example that if you start with formaldehyde, methanol is what you're going to get as your product when you use one of these reagents. Now, let's say if your starting material is another aldehyde, it's any other aldehyde but formaldehyde, it's not formaldehyde but any other aldehyde, then your product is a primary alcohol always. It has the same number of carbon atoms. And so essentially, if I start with any other aldehyde and we do this reaction, again, I'm going to use this example of sodium borohydride. Okay. The mechanism with lithium aluminum hydride is not very different. There are several similarities here, but that gets pushed over. O minus. Okay, and realize at this point there are two hydrogens here, which we do not have to show. So we've converted that aldehyde into an alkoxide, and this alkoxide in a subsequent step, mechanistically it's a subsequent step, it's going to get protonated. So we'll get that alcohol, but I've just basically moved that oxygen up. So we get that alcohol plus we would get methoxide. And when you do a workup, again, there is a workup here. So when you do the workup, the methoxide gets protonated to methanol, back to methanol. But if you look at it, we started with an aldehyde and we've got what we have here is a primary alcohol. And essentially, this carbon, which was the carbonyl carbon, the carbon with the double bond O to it, is what became the alcohol here. Okay, so all you have to do is you have to get rid of that double bond and put an alcohol, the double bonded oxygen, convert it into an alcohol to write your product if you're starting from any other aldehyde. Similarly, when you start with ketones, okay, so formaldehyde gives you methanol. Any other aldehyde would give you a primary alcohol. If you start with a ketone as a starting material here, your product is always going to be a secondary alcohol. So when you start with a ketone and you do this reaction, okay, the hydride comes and attacks. There's a negative charge over there. This double bond goes up. R prime. There's hydrogen over there. There's the alkoxide. And then in the next mechanistic step, this can go deprotonate. And so it would give us the secondary alcohol. I basically hit that hydrogen because we're working with bond line structures, plus methoxide. And again, when you do that workup, the methoxide gets converted into methanol. Okay, so, but what I wanted to illustrate here is that, again, like I said, the carbonyl compound, okay, the nature of the carbonyl compound determines the alcohol product, the nature of the alcohol product that's formed. Formaldehyde gives you methanol. Any other aldehyde is converted into an alcohol, and ketones are converted into secondary alcohols. And this is very important because we're going to be learning another class of a nucleophile that could attack carbonyl compounds and give you alcohols from there. And we'll notice that that's in stark contrast to what we see with the hydridic reagents. Okay, so I hope that was helpful.